Suppose we have a differentiable function of two variables, and that's defined in a region that contains a smooth curve, such as this circle. And the curve is defined by the position vector as a function of the parameter t, with the horizontal component in the I direction and the vertical component in the j direction. And if we have some point on this curve where the function has a local minimum or a local maximum, and the local minimum or maximum of the function are relative to the function's values on the curve, then the gradient of the function is orthogonal to the curve at this point, where the function has a local minimum or maximum. And we can show this using the chain rule by differentiating the function with respect to the parameter t. So that's the partial of the function with respect to x by dx dt, plus the partial with respect to y by dy dt. So that's equal to the gradient of f by the tangent vector, being the velocity vector. And at a local minimum or maximum, this derivative is equal to 0. So therefore, the gradient vector is orthogonal to the curve at this point. And similarly, if you add a z component, you'll get a similar result for a function of three variables. So this leads us to the Lagrange multiplier method, which is a powerful method for obtaining an extreme value of a function subject to a constraint. So if we have a differentiable function of two variables and another differentiable function of two variables with the gradient of the function g being not equal to 0, then we can find the local minimum or local maximum values of the function f that's subject to the constraint g of x and y is equal to 0. So this is the constraint, provided the local minimum and maximum values exist, by finding the values of x, y, and an additional parameter, lambda, being the Lagrange multiplier, that simultaneously satisfy the following two equations, being the gradient of f is the Lagrange multiplier by the gradient of g, and the equation for the constraint, which is g of x and y is equal to 0. So as we showed before, the gradient of the function is orthogonal to a curve defined in the interior of its region at a point that's a local maximum or minimum relative to other values of the function on the curve. And if we suppose this curve is defined by the function g of x and y is equal to 0, then that makes it a level curve of the two variable function g. So given it's a level curve of this function, then the gradient of the function g is orthogonal to the level curve at all points on the curve. So therefore, at a local maximum or minimum, the gradients point in the same direction, and therefore the gradient of f is a scalar multiple of the gradient of g. And this definition applies to functions of three variables. So instead of a function of x and y, you'll have a function of x, y, and z, and the function of the constraint is also a function of x, y, and z. And similarly in that case, you'll find the values of x, y, z, and the Lagrange multiplier that satisfy these two equations. So let's make a bit of space and show how the Lagrange multiplier method works. So if the function defining this surface is x by y, and we want to find the maximum or minimum values of the function on the curve defined by the function of two variables, being x squared plus y squared minus 1 is equal to 0. So effectively we're finding the minimum and maximum values of the function f subject to the constraint g of x and y, which according to this equation is a circle of radius 1. So essentially we're constraining the maximum and minimum values to be found on this curve rather than the function's entire domain. So what we do is take the gradient of f, which is y in the I direction, plus x in the j direction, and the gradient of g is 2x in the I direction, plus 2y in the j direction, and equating the gradient of f with the Lagrange multiplier by the gradient of g. So we're just basically multiplying the gradient of g by lambda. So for the x component, we get y is equal to 2x lambda, and equating the j components, we get x is 2y lambda. And if we substitute for x in this equation, we get y is 4 lambda squared multiplied by y. So for this equation to be satisfied, lambda is equal to plus or minus a half, such that we get y is equal to y on both sides. And if we substitute for lambda in this equation, we get y is 2x by plus or minus a half, so therefore y is equal to plus or minus x. And now we can substitute for y in the constraint equation. So we get x squared plus or minus x squared minus 1 is equal to 0 or is equal to 1. So that gives 2x squared is equal to 1. And solving for x, we get x is plus or minus 1 on root 2. And given y is plus or minus x, then what we get are 4 points on this circular curve that are local minima or maxima. So these are x is equal to plus or minus 1 on root 2, and y is positive 1 on root 2, and the other 2 points are x equals plus or minus 1 on root 2, and y is negative 1 on root 2. So according to this equation, the local maximum is 1 on root 2 by 1 on root 2, which is a half, and this occurs at the points with an x coordinate of 1 on root 2 and a y coordinate of 1 on root 2, and also an x coordinate of minus 1 on root 2 and a y coordinate of minus 1 on root 2. So as we can see, when we map this circle to the surface, we can see that the local maximum occurs at these 2 points. And the local minimum is minus 1/2, which we can observe from this function. So that occurs at the points with a positive x coordinate and a negative y coordinate and a negative x coordinate and a positive y coordinate. So that's this point and this point. So when we map this circle to this surface, the local minimum occurs at these 2 points. And now if we look at this point over here, being the local minimum, with an x coordinate of 1 on root 2 and a y coordinate of minus 1 on root 2. So the gradient of f at this point is the y coordinate, being minus 1 on root 2 in the I direction, plus the x coordinate, which is 1 on root 2 in the j direction. So the gradient of f is orthogonal to the circle and points in this direction. And we see the gradient of g is 2 by x, which is 2 on root 2 in the I direction, plus 2y, which is minus 2 on root 2 in the j direction. So the gradient of g is also orthogonal to the circle and points in this direction. So it's antiparallel to the gradient of f and has twice the magnitude of the gradient of f. Hence this Lagrange multiplier of a half, which in this case is negative a half by this equation, because the two gradient vectors point in opposite directions. And furthermore, we can see the circular curve is tangent to the level curve at the local maximum. So recall the gradient of f along a level curve of f is perpendicular to the level curve at every point on a level curve. Suppose we have a differentiable function of 3 variables, being x, y, and z, and this is subjected to 2 constraints, being g1 of 3 variables is equal to 0, and the second constraint is given by the function g2, being also a function of x, y, and z, and that's also equal to 0. So these two constraint functions are both differentiable, and the gradients of both functions are not parallel. So the gradient of g1 is not parallel to the gradient of g2. Then what we're looking for are the constrained local extrema, being the local minima and local maxima of the function f, by finding the points having coordinates of x, y, and z where the function has extreme values. So these points are constrained to a curve or surface in the function's domain. And to find these points where the function has extreme values, then we're looking for values of x, y, and z, and additionally a Lagrange multiplier for the first constraint and a multiplier for the second constraint, where the values satisfy the following equations simultaneously. So we have the gradient of f is a linear combination of the gradient of the first constraint and the gradient of the second constraint. And the other equations that need to be satisfied are the constraint equations. So let's visualize this in an example. So if we want to find the closest distance from the origin to a point in space, so our function in this case is x squared plus y squared plus z squared, which gives the squared distance from the origin to a point in space. And our constraint is the equation of the cone. So we have x squared plus y squared minus z squared is equal to 0. And the other constraint is the equation of the plane, which is y plus z minus 1 is equal to 0. So we're looking for the closest distance of a point to the origin where the point lies on the curve that's formed from the intersection between the plane and the cone, which we know is a parabola. And we want to find the points on this curve where the function f has local maximum and minimum values relative to the function's values on the intersecting curve. So recall at a local maximum or minimum, the gradient of the function f is normal to the intersecting curve. So recall we showed this previously by the chain rule, where we differentiated the function with respect to the parameter t, that parametrizes the curve, and that was equal to the dot product between a gradient of f and the tangent vector to the curve, and this derivative is equal to 0 at the point where the function has an extreme value, then the gradient of the function is normal to the curve at this point. And given that the curve lies in both surfaces, so it's on the cone and the plane, and given that g1 and g2 are the equations of level surfaces to these two functions of three variables, then the gradient of the cone, being g1, is also perpendicular to the curve, as it lies in the surface of the cone, and similarly the gradient of g2 is also normal to the curve, as the curve also lies in the surface of the plane. So therefore these gradients lie in the same plane, and the gradient of f is a linear combination of the gradients of the two constraint functions. And note that in this case, we'll see that the cone constraint is not even required, because the gradient of the plane is parallel to the gradient of the function f. So let's make a bit of room here. So the first step is to take the gradient of f, which is 2x in the I direction, plus 2y in the j direction, plus 2z in the k direction, and taking the gradient of the first constraint and multiplying by the Lagrange multiplier, we get 2x lambda in the I direction, plus 2y lambda in the j direction, minus 2z lambda in the k direction. And taking the gradient of our second constraint function and multiplying this by the other Lagrange multiplier, we get 0 in the I direction and 1 multiplied by mu in the j direction, plus 1 multiplied by mu in the k direction. And now we can equate the I components, so that gives 2x is equal to 2x lambda. So that's according to this equation. And the j components give 2y is equal to 2y lambda plus mu. And let's make a bit of space. And for the z components, we get 2z is minus 2z lambda plus mu. And now we're looking for values of x, y, and z, and the two Lagrange multipliers that satisfy these three equations and these two constraint equations at the same time. So here we recognize that the first equation is satisfied when x is equal to 0, or where x is not equal to 0, and lambda is equal to 1. And with these two equations, we can do a bit of algebra and write 2y by 1 minus lambda is equal to mu, and 2z by 1 plus lambda is equal to mu. And if we divide them together, we get y on z by 1 minus lambda on 1 plus lambda is equal to 1, which eliminates mu, and therefore we can write y is 1 plus lambda on 1 minus lambda by z. So from this, we can conclude that lambda is not equal to 1, so therefore we have x is equal to 0. And then from these two constraint equations, we can now solve for y and z. For x equals 0, we have y squared minus z squared is 0, and y plus z is equal to 1. So solving these two equations, we find the y coordinate of our point being 1/2, and the z coordinate is also 1/2. So this is the point where the function takes on the extreme value, being the minimum distance of a point on this parabola from the origin. So this point has the following coordinates. So at this point, given y is equal to z, then lambda is equal to 0. So therefore, we didn't really need the constraint g1 to find the minimum distance from the origin, because that's actually the closest point on the entire plane to the origin. So therefore we see the gradient of f is 0 by the gradient of g1 plus mu by the gradient of g2, which from one of these equations, where y is equal to a half and lambda is equal to 0, we have mu is equal to 1. So the gradient of f has components of 2 by 0, 2 by a half, and 2 by a half. So it points in the positive y and z directions. And the gradient of g2 is perpendicular to the plane and has components of 1 and 1. So it points in the same direction as the gradient of f and has the same magnitude. So as you can imagine, at a distance from the origin to this point, from this equation, where x was 0 and y is equal to a half and z is equal to a half, then the squared distance to this point is 1/2. Well, we can write this as 1 on root 2 squared. So this gives a level surface, being a sphere. So this specific sphere is a level surface of the function f, and therefore the gradient of f is perpendicular to this surface. Find the dimensions of the rectangle with the largest area that can be inscribed in the given ellipse. So in this case, our objective function that we want to maximize, which gives the area of the rectangle, is the length of the rectangle, which is 2x, by the height, which is 2y, so that gives 4xy. And our function for the constraint, being g of x and y, is the equation of the ellipse set to 0. So we'll just subtract 1 from both sides and set this equal to 0. And now we find the gradient of f, which is 4y in the I direction, plus 4x in the j direction. And the gradient of g is 2x on 16, or x on 8, in the I direction, plus 2y on 9 in the j direction. And using the following relationship between a gradient of f and the gradient of g, so that's the Lagrange multiplier by the gradient of g, and equating the x and y components, we get 4y is equal to x on 8 by lambda, and 4x is 2y on 9 by lambda. And now we want to find x, y, and lambda that satisfy these two equations and the constraint equation. So if we divide these equations together, we get y on x, and that's equal to x on 8 on 2y on 9, which gives 9x on 16y, and the lambdas cancel. So if we multiply through by y and multiply through by x and take the square root of both sides, we get y is 3 on 4x. So here we've taken the positive root because the dimensions of the rectangle are both positive, such that the area is positive. And now substituting for y in the constraint equation, we get x squared on 4 squared plus y squared, which is 3 squared by x squared on 4 squared, and y squared is divided by 3 squared. And adding 1 on both sides, we get the following expression. And cancelling 3 squared and multiplying through by 4 squared, we get 2x squared is equal to 16, or x squared is equal to 8. So that gives x is plus or minus 2 root 2, and we'll take the positive root. And now if we substitute for x in this equation, we get y is 3 on 2 by root 2, or 3 on root 2. So therefore the largest horizontal dimension of the rectangle is twice that of x, so that will be 4 root 2. And the largest vertical dimension is 2 by 3 on root 2, or 3 root 2. Find the closest point on the plane to the given point. So our objective function is the squared distance to the point, which is a function of 3 variables. So that will be x minus 2 squared plus y minus the y coordinate squared plus z minus the z coordinate squared. And our function for the constraint is also a function of 3 variables, and that's equal to the equation of the plane set to 0. So we just subtract 10 from both sides. So the closest point we're looking for is constrained to lie on the plane. So taking the gradient of f, we get 2 by x minus 2 in the I direction, plus 2 by y minus 1 in the j direction, plus 2 by z minus 2 in the k direction. And the gradient of g is 1 in the I direction, plus 1 in the j direction, plus 2 in the k direction. And now using our equation, where the gradient of f is a scalar multiple of the gradient of g, where the scalar lambda is the Lagrange multiplier, we equate the x, y and z components. So what we get is 2 by x minus 2 is equal to lambda, and 2 by y minus 1 is also equal to lambda, and 2 by z minus 2 is equal to 2 lambda. And we're looking for values for x, y and z and the Lagrange multiplier that satisfy these equations and the equation for the constraint simultaneously. So we can equate the first two equations, which gives 2 by x minus 2 is equal to 2 by y minus 1, and cancelling the 2, we get y is equal to x minus 1. And we can also write z in terms of x by multiplying the first equation by 2 and then equating this with the third equation. So we get 4 by x minus 2 is equal to 2 by z minus 2. So dividing through by 2, we get 2 by x minus 2 is equal to z minus 2, and therefore z is equal to 2x minus 4 plus 2, or minus 2. And now we can substitute for y and z in the constraint equation. So we get x plus x minus 1 plus 2 by z, which is 4x minus 4. And adding 10 to both sides, we get the following expression. So if we simplify this, we get 6x is equal to 15, and therefore x is equal to 15 on 6. And then if we substitute for x in this equation, we get y is 15 on 6 minus 1, which is 6 on 6. So therefore y is 9 on 6, or 3 on 2. And substituting for x in this equation, we get z is 2 by 15 on 6, which is 15 on 3 or 5, minus 2, so that gives z is equal to 3. So the closest point on the plane to this point has coordinates of 15 on 6, 3 on 2, and 3. And you can substitute these values in the constraint equation to verify it's satisfied. Find the extreme values of the function on the circle that's formed by the intersection between a plane and a sphere. So our first constraint equation, which is also a function of 3 variables, is the equation of the plane, and our second constraint equation is that of the sphere, which will subtract 4 from both sides to get g is equal to 0. So the first step is to find the gradient of f, which is y in the I direction, plus x in the j direction, plus 2z in the k direction. And the gradient of the first constraint function is minus I plus j. And the gradient of the second constraint function is 2x in the I direction, plus 2y in the j direction, plus 2z in the k direction. And they're using the following relationship, where the gradient of f is a linear combination of the gradient of g1 and the gradient of the second constraint function, where lambda and mu are Lagrange multipliers. We can equate the I components, so we get y is equal to minus lambda plus 2x mu, and the j component gives x is equal to lambda plus 2y mu, and the third component gives 2z is equal to 0 lambda plus 2z mu. And what we're looking for are values of x, y, and z, and the Lagrange multipliers that satisfy these equations, and also the constraint equations. So firstly, we'll look at the case where z is not equal to 0, meaning that mu must be equal to 1 in this case. So from the first two equations, we get y is minus lambda plus 2x, and from the second equation, we have x is lambda plus 2y. And adding these equations together, we get y plus x is 2x plus 2y. So that gives y is minus x. And if we substitute this into the first constraint function, we get minus x is 0, so x is equal to 0. And y is equal to minus x, so that means y is also 0. And substituting these into the second constraint function, we get 0 plus z squared, and adding 2 squared to both sides, and taking the square root, we get z is equal to plus or minus 2. So therefore the extreme values occur at the points with x equals 0, y equals 0, and z is equal to plus or minus 2. So that's our first case. And now let's make a bit of room. And for our second case, we take z is equal to 0. So mu is not necessarily 1. So from the second constraint equation, we have x squared plus y squared is equal to 4. And from the first constraint equation, we have y is equal to x. which if we substitute in this equation, we get 2y squared is equal to 4, and therefore y is plus or minus root 2. And from this equation, x is also plus or minus root 2, and we have z is equal to 0. So therefore our other extreme values occur at x is plus or minus root 2, and y is plus or minus root 2, and z is 0. And now to find the extreme values, we just substitute these coordinates into the function. So we have f of 0, 0, and plus or minus 2. So that gives 0 by 0 plus or minus 2 squared, which is equal to 4. And to find our other extreme values, we just substitute the coordinates of these points into the function. So we have f of root 2, and 0. So root 2 by root 2 is 2. And our other point is at minus root 2, and 0, which also gives 2. So the maximum of 4 occurs at these 2 points, and the minimum of 2 occurs at these 2 points.